So thank you for joining us. My name is Ela and I'm the organizer of the meetup. I would like to say a big thanks to Amit and Emma from Amazon and Ming for accepting our request to come here. Thank you. Afik and Daniel from eviCore was here to present too. And honestly, I'm very excited to hear the talks of this meetup and the next meetup. So welcome and enjoy. Thanks. Amit.
Okay, so hi, good evening, everyone. My name is Amit Schwartz. I am a software development manager in Amazon, part of the Alexa machine learning platform team. Me and Ming are going to present Alexa today. I will give a zoom out about Alexa, how Alexa is working, the different algorithms that run inside Alexa, a little bit about the sequence and data flow, and then we will zoom in and drill down into the wake word algorithm, and Min will do this part. Okay, so Alexa, what's playing? So what are we going to talk about? We're going to talk about what is Echo, what's Alexa, what is Alexa skill kit and voice service, what makes Alexa tick. This is going to be the main part. And then we're going to go quickly about what people are saying about Alexa and what will you ask. So let's start with Echo. What is Echo? So Echo is a Wi-Fi connected device designed for voice interaction. As you can see, it has 7 microphones that allow it to hear you even in very challenging acoustic conditions. It has a pair of speakers, woofer and tweeter, that provide 360 degrees surround sound. And it is connected to the Alexa voice service in the cloud. And with Echo, you can do different things. You can listen to music. You can play a music by song, artist, genre, from Amazon Music, Spotify, or Pandora, or any other place. You can play audiobooks. You can listen to radio station, hear news brief from different providers like BBC or NPR News. You can manage your task. It is connected to your Google Calendar, and you can create meeting. You can manage your to-do list, set alarms, set timers, ask for the weather, for traffic report. You can call people or send messages hands-free. You can create shopping list. You can ask any question, general question. Alex, she knows a lot of things. If you have automation, you can control your smart house with Alexa and many, many more things. So let's start with a short clip that shows all of that.
Say hello to the all-new Echo. It's everything you love about Echo with a brand new look and a brand new price. Echo connects to Alexa to play music, call friends and family, control smart home devices, and more. And because Alexa is in the cloud, she's always getting smarter and adding new features. Echo comes in 6 unique styles designed to blend in or stand out. And with immersive 360-degree audio, it can fill any room with crisp vocals and rich bass. 7 microphones help Echo and Alexa hear you from any direction, even when music is playing. All you have to do is ask.
Alexa, play my Sweet Victory playlist everywhere.
Okay.
Alexa, turn it up.
Alexa, play my messages.
Hey babe, please don't touch the macaroons. They're for the baby shower.
Alexa, what's a macaroon?
A macaroon is a type of small circular cake, typically made from ground almonds.
Wow! Alexa, remind me to sign Emily up for soccer.
Okay.
Alexa, drop in on the living room. Hey babe, just finished the nursery.
Perfect. Timing. We need to go.
Wait, what?
Alexa, turn on the hall lights.
Okay.
Alexa, lock the door.
Okay.
Ugh, okay, man, one more. Alexa, how much time is left on the pizza timer?
There are about 4 minutes left on the pizza timer.
Okay, you're on.
Alexa, party time.
Excellent.
The all-new Amazon Echo.
Okay, so Alexa is getting smarter every day. New capabilities are added constantly.
Introducing Echo Plus. It's everything you love about Echo, now with a built-in smart home hub. Echo Plus.
Okay, sorry. So we are adding more and more capabilities, and just ask Alexa to control your TV, request Uber or order pizza. It can do a lot of things. So, okay. So what is the Echo device design? So the philosophy is to keep the design simple, implement features in the cloud when possible, and make the device application agnostic and the application agnostic to the device. So basically you can run Alexa on any Echo device or even third-party devices that use it. In the Echo, we have few functionalities or features. We have the wake word engine. We're going to talk about it soon. Beamforming, echo cancellation, audio streaming, and Bluetooth and Wi-Fi. So it's very, very simple, and most of the logic is implemented in the cloud. This is the Echo family. We have the Echo Dot, which is like the Echo, but with simpler speakers. The Echo that we just saw, this is the Echo Plus, that contains also an IoT hub built in. So if you have home automation, you can control it from there. It has Zigbee and Bluetooth capabilities to control your home devices. We have the show here on the right, which is also has a screen, LCD screen, that you can also receive information, not only voice, but also see picture and interact with it. So if you ask for, I don't know, for play the Beatles, it will show you a list of the Beatles records. Then you can select a record and track and interact it either by voice or by touch. And this is the new Echo Spot that is going to be released at the end of the month, I think. Going to be already released, going to be available at end of the month, which is like a small alarm clock near your, you can put near your bed, and you can have video chat with it, you can interact with it. It's a very cool and nice device. So what's the difference between Alexa and Echo? Echo is actually the device, and Alexa is the software or the service that runs inside. You can find Alexa also in other places. So for example, we just released a Fire tablet, which works with Alexa, so you can interact with it hands-free. Fire TV, I think, already supports Alexa as well. We have integration with different speaker vendors, and BMW just released Alexa integration, so you can drive your car and interact with it using speech. So now I would like to explain how Alexa is working. So let's walk through the sequence of events that occur when user utters a phrase such as, Alexa, what is the weather? Okay, so at the beginning in Alexa, in the device, we have a wake word engine. This engine listens all the time and waits to hear the word Alexa. Okay, once it hears Alexa, it will stream the utterance to the cloud. Okay, you can see once you say Alexa, you're going to see a light on the top of Alexa, and then it will send the information to the cloud. And it will reach the speech platform. Okay, the speech platform will send the voice to the automatic speech recognizer, ASR, and the ASR will be responsible to convert the data, the sound, into text. Okay, the ASR will return actually multiple results because it's with different significance. So it will return the n best results for this voice. Okay, the recognition result. Once we have the recognition result, the message is sent to the NLU. NLU stands for Natural Language Understanding. Here, these are the algorithms that run and try to understand what the user meant. Okay? Later we will drill down into each module. The NLU, the first thing we need to find is what is the intent classification. That means what the user wanted to do. In our case, what's the weather? It's a weather forecast intent. Okay, there are different type of intents. So it will find what is the intent classification, and also add all the relevant attributes to it. Okay, so the NLU will return an intent, and then the speech platform will send it to the relevant skill or application. There are many, many skills and many, many applications. Each one knows how to handle specific type of intent. Okay, and in this case, it will send it to the weather forecast application, and that will return a speak directive that contains some kind of text that explains what is the weather today. Okay, the text will be sent to the text-to-speech engine, TTS, that will return a voice. Okay, the text-to-speech, we send something called, as you can see, it's called SSML, which contains also not only the text, but also metadata about the text. For example, is it a question so Alexa will not be sounded like a robot. It will sound like human. So you can add emotions, you can add to explain Alexa how to pronounce this sentence and how to say it. This information will be sent down to the Echo device, then it will return the reply. Everything will happen in milliseconds, very, very fast, and everything will be done in parallel. That means the ASR will return multiple results. The NLU will also return multiple results because maybe the question is relevant to multiple skills. And the speech platform will need to rank and find what is the best match based on the score that each one returns and based on the context. Okay, so the speech platform also manages the session and the dialogue. So if you have a conversation with Alexa, it knows the context and dialogue. And sometimes, for example, if I ask Alexa, what is the weather? And then I will say, Alexa, and tomorrow, it will automatically know that you are asking about the weather in Boston. Okay, so there is a context of the message that the speech platform is managing. Question about, yes?
So all this is in cloud?
Everything is in the cloud. So this is not in the cloud. So the WakeWord engine is on the device itself. Just listen to the word Alexa and the sentence that come afterward, and it will send the voice to the cloud. Everything else is done in the cloud.
So for the dialogue manager, how do you deal with it knowing when you ask a question, like you know that it's talking to something new, or referring to the context from the previous question?
So this is the dialogue in session. We keep the context. We save the context, and so every time you ask something, there is a session. So when you follow up with a question, we see, okay, are we still part of the session? And then we look for that information.
What if like person ask a new question? You need to know that they're asking something new versus something.
So I'm not part of the dialogue management, but I can tell you that usually there is a time factor. So it checks if it's relatively close, okay, to the previous question, and also if it's relevant. If it's a totally different question and the dialogue information is not relevant, then it's not relevant. It will not use it. Okay. So now let's look on another use case. This time I will tell Alexa, play Message in a Bottle by Sting. Okay. So the beginning is done the same. The WakeWord engine will listen and hear the word Alexa. It will forward the voice to the speech platform. The speech platform will send my text to the ASR, the automatic speech recognition, that will return a recognition result. That will be sent to the NLU. NLU stands for stands for the natural language understanding. It will say that this is a play music intent. Okay, it will say that it's a play music intent, and I'm looking for a song called Message in a Battle by an artist called Sting. Okay, I can tell you that here in the background we also have catalogs of information, that we have all the available song and singers, so we can identify if this song really exists or not. And if not, maybe we will suggest and provide another song by Sting or something like that. But it also uses a catalog. We have many catalogs for many different subjects. And it will go to the play music application or play music skill. And the play music skill will not return a speech, it will return a URL. Okay? So it will return a play directive that will be sent to the Echo device. The play directive contains a URL, and the Echo device will download the song from this URL and play the song. In parallel, the Echo device is sending events to the speech platform. So, for example, there is a playback started, playback nearly finished, and playback finished event. And this is a very interesting point that I would like to talk about. And it's interesting to see that the Echo device is not aware of a playlist or what I'm asking. Okay, and this is part of the philosophy we told, that we will keep the Echo device as simple as possible and we move all the logic to the cloud. So before the song ends, it will send a playback nearly finished event to the speech platform. The speech platform will call the play music skill. Play music skill will say, okay, so the track 1 is about to end. Let's play track 2. It will send a new play intent to the Echo device. Okay, so while the song is playing, the Echo device will start to download the new song. Okay, and then when the first song ended, the second song will start automatically, without any, quickly, and everything will, because it already downloaded it in the background. And the Echo device is as dumb as possible. All the logic is in the cloud. Okay. Yes.
So how much state is it keep track of? You say to it, play the song. While the song is played, you say, play something a little more upbeat. Is it able to figure out what song it was playing? Does it have enough history to go do something like that?
So again, I'm not proud of so there are, as you see there, it's very modular, and there are different tips that handle different things, different skills, and I'm not working on the Amazon Music part, but there are a lot of, again, our goal is to have a frictionless experience. So if you will ask for a song that does not exist, okay, it will find, let's say I ask for a song by Sting that doesn't exist because he didn't understand me. It will offer you, would you like to hear this song by Sting? It will try, it's called recovery. We try to provide you an answer. We try to, we know, for example, what you listened to before, what you like. Sometimes when my son talks to Alexa, I have a 3-year-old one, she tells him, this is a song you might like. Okay. Last week we even released speaker ID features, so we know your preferences, not only by account, but by a person in the family. Okay, so we try to make everything smart. I don't think we have models per person, but we use the data that that you speak to Alexa, we use it to train our models. And we have many models for different regions and accents, etc. There are some even, I think there are also some personal models, depends on, your audiobooks and things like that, but not for ASR. So I think for shopping, you need to enter a password. I think you need to approve it from the application. There is no authentication in Alexa yet. Okay, I'll move on. We have more question at the end, okay? Alexa is voice-centric, but it's not voice only. There are some applications that have a web interface, okay, either the mobile application, the Echo Show, or the Echo Spot. I will go quickly. Alexa knows a lot of things. So you can ask a simple question like, how tall is the Golden Gate Bridge, sorry. This is a simple question to answer. But you can also ask more complex question like, who was the president when Queen Elizabeth was a teenager? Okay, so in order to answer that, Alexa first needs to find who is Queen Elizabeth, how old is she, when was she a teenager, and then find who were the president that time. So it knows also how to answer complex questions. Alexa Skill Kit, it's basically the way for third party to add skills to Alexa. So it's a set of APIs and documentations and your ability to develop your own skill, and then deploy it to Alexa. I think we have more than 25,000 skills, and the number is growing. For example, I'll give you an example. This is a StubHub. Okay, so Alexa, ask StubHub what is going on tonight.
I found several events in Boston in the next 7 days. Here are the first few. 1. Zed at House of Blues on October 18th. 2. Fun Home at the Boston.
Alexa, stop. So this is an example of an integration, okay, that StubHub developed, and there is a skill set that many people can develop. We have, if you want to order pizza, Uber, many integrations that basically call API on the StubHub, to the StubHub services, and they can extend and add functionality to Alexa. Another way to integrate with Alexa is with the Alexa voice service. So this is if you manufacture any device that has mic and speaker, you can integrate Alexa into it. Okay, so we see some microphone manufacturer are now embedding Alexa into it. Alexa is being added into cars, etc. So these are two different ways that you can integrate with Alexa. So what makes Alexa tick? What makes it work so quickly and so nicely? So one of the core things is the pervasive use of deep learning. We use deep learning everywhere, for example, in wake words, speech recognition, NLU. Deep learning requires a lot of data to train the deep network, neural network. And I'm part of the machine learning platform team, and there are thousands of servers that are calculating thousands of machine learning algorithms all the time on a lot of humongous amount of data. Algorithms are being deployed every day. Some algorithms are calculated and deployed daily, trained and deployed daily. So behind Alexa, there is a humongous amount of data and compute power that supports it. And this is why it also grows and new functionality is added and it is improving every day. So let's talk about some of the algorithms we use. Again, it will be a little bit high level. Later we will dive deep into one of them. The first thing I want to talk about is beamforming and acoustic echo cancellation. Okay, so this is an algorithm that runs on the device. So let's press play. So Alexa is playing a music and someone is saying Alexa. You can see that it's very hard to understand what he says. So the beamforming and acoustic echo cancellation basically clears the data and leaves only, mostly clears the sound that Alexa is doing, the music or the speak that Alexa is doing. So now it sounds, this is how it sounds after the algorithm is running. Okay, this is done also using deep neural network. Another thing is the wake word detection. Okay, we listen to a lot of words. We need to identify when someone says Alexa. There are many challenges around the signal quality. For example, the sound noise ratio can be problematic. They are competing. There are more sounds in the background, music playback, pronunciation. Different people pronounce Alexa differently. There is something called accuracy versus latency. We want it to work very accuracy and very fast, which is very challenging. I'm not gonna we're gonna talk about this algorithm to the mathematics behind it in a few minutes. The far field, the ASR, the speech recognition, is also another challenge. The acoustic challenges are the same as the wake word, okay, low SNR, etc. There is a large vocabulary of words. Okay, it's not only the words from the dictionary, it's also, think about it, all the songs, movies, sports events, sport teams, anything that happens in politics. So the vocabulary is changing and growing. Artist names are sometimes not standard. We compare the names to the name of to a catalog. Okay, and sometimes in the catalog, for example, Pink, this is how she writes her name. So it's very, very challenging so there are many, many challenges. So also the catalog data is not always so easy to use. And there are also a confusing title. For example, Sundays versus Sunday. And it's very, very hard to find all these issues. So we run mainly neural network algorithms for ASR, but also additional statistical models to resolve this issue. Natural language understanding, also to understand what was the intent of the user. Also here we have many algorithms around understanding what they want. So sometimes there is cross-domain intent. So for example, play remind me versus remind me to go to the play. It's the same words, but totally different intent. And I can tell you that Alexa will try both of them. Each one will return a score, and this is how we select what to use, or it's going to be based on the context. Robustness of ASR errors. So let's say user select play songs by Michael Jackson, but the ASR can return play songs by Michael Jackson. Okay, so there can be spelling mistakes. Okay. So another problem with the natural language understanding is that there is no UI. So we need to be very accurate. We cannot present you 10 results and you will select, okay, I want number 3. We need to return one result, and that result should be the correct one. So it's very, very challenging and hard. So we run, for NLU, we use combination of statistical models, of rules, which are FSTs, graphs that we build to understand the language based on the language rules, okay, and also neural networks. I will skip that. Dialogue management, I think we talked about it. We have different error recovery strategies. For example, if you say Alexa, Bruno Mars, I didn't say what, okay? But it will check and see statistically that Bruno Mars, usually you don't want to see the Bruno Mars value in Wikipedia, you want to hear songs for Bruno Mars, and she will tell you, okay, shuffling song by Bruno Mars. Okay, so there are many error recovery strategies based on your preferences and other preferences. What people are saying about echo. So this is from the media. There's no gadget dream greater than this. Your wish is my command. I don't think I can go back to remotes and apps after trying the Echo. This is how controlling music at home should work. Controlling, now you can also control the TV with Alexa. I just spoke to the future and it listened. Okay. Our customers, we have a score of 4.5 in Amazon. It's life-changing. Echo saved my mother's life. Echo is changing my life for the better. Most quality of life improving tech I have ever bought. So people really, really love it. And this is the interface of the future. So now, if you have any questions.
I'll try to bring the microphone because we are capturing.
Yes, you mentioned for the skills kit, there was 25,000 skills currently. And how does my skill, if I want to add a skill to Alexa, how would it get selected over one of the other 25,000?
So I think that today, one way is that there is an activation word for skill. For example, for StubHub, I said, Alexa, ask StubHub what is going on tonight. So I directed Alexa what skill I want to use. So this is how it's done today. We are working on making it more natural and more easy. This is what I can say.
Excuse me. What kind of neural net algorithms do you use? Convolutional networks? And the other question is, what do you use in the back end? TensorFlow, your own, etc.?
You want to answer that? So, Ming is from the science team. I think he can answer more accurately.
Maybe when Ming will give a more technical presentation later. Who else?
Hi. So for your intent detection, like when you get it wrong, how can you tell? And do you have triagers who label the data again when Alexa predicts the wrong intent?
So, first question: how do we know that we were wrong? This is a very good question, and it's another thing that we work on finding. So, one thing is, for example, if we ask something and you immediately, after 1 second, you ask something else. There is something we call sentiment. We can measure, your sentiment, if you're happy or not happy with the result. You say, Alexa, stop, Alexa, no. So there are things there are some signs that we use to find, is it an error or not?
Hi. For the beamforming and the acoustic echo cancellation, did you say you use neural networks for that too, or do you use signal processing techniques on the device to kind of solve them?
You want to answer this?
Yeah, I think nowadays the mainstream is to switch to neural network. But we couldn't let you know the exact algorithms we are running. But as you may see from everywhere else, people are switching to the neural network for these kind of tasks.
How much?
Yeah, last question, and then we'll have another.
How much do you, if at all, do you use the history on the device to help with speech recognition and intent recognition, or if at all? So if I always want to order pizza instead of listen to music or whatever, how much do you or does it, have you just found that it doesn't pay to do that because
it depends on the domain, but I will give an example of shopping. Okay, Alexa Shopping is one of the domains, and their goal is to be your personal assistant. They want to know everything about you, what you like. And when you will want to buy a pair of socks, they will already know that, or toilet paper, they will already know that last time this is the brand you like, and they will offer you the same thing. So I think it depends on the domain. And for example, shopping, their goal is really to know what you like and what you prefer, and they will collect the information about you to help you and to provide you, because again, it's not Amazon that can provide you 10 options. We can provide you one, maximum 2 options. So really to help you and to be your personal assistant as much as possible. Okay, thank you very much.
My name is Ming. I'm working at Amazon Alexa Machine Learning, focused on the weak word detection. Tonight, I'm very happy to be here talking about our work. Amit has already given a great overview of the Alexa and Echo devices. In my talk, I will focus on the weak word detection part and dive deep into how we apply the deep learning techniques to improve the weak word detection. My talk is based on a externally published paper at InterSpeech, which is a major speech conference this year, titled Compressed Time Delay Neural Network for Small Footprint Keyword Spotting. This is joint work with our colleagues David, Yixin, Varun, Mike, Panchi, Nico, Spiros, and Shiv. David is currently a PhD candidate from Johns Hopkins, and he performed this work during his internship last year. My talk will have the following sections. First, I will give an introduction on the hidden Markov model-based keyword spotting system. And the second part focuses on introducing the time delay neural network and how we compress this network using techniques such as subsampling of temporal connection, inserting bottleneck layers to reduce the complexity of the system. The third part summarizes our training recipes for the TDN neural network, including the techniques like transfer learning or multitask learning. Experimental results are presented in the next session, and the last part is for the conclusion. Here, this picture shows a typical use case for Alexa. Here, with the Echo Dot sitting on the stand, our customers could directly speak, Alexa, what's the weather? And here we deploy a keyword spotter running constantly on the Echo Dot devices, and it works on detecting the specific weak word Alexa. Once this Alexa word is detected, and there will be a light on the top, and the device will stream the customer's speech into cloud for further processing, like speech recognition or language understanding, dialogue management, etc. Here we can see this weak word detection is a very important feature for Alexa, as that's the first step our customers interact with Alexa devices. In order to make this keyword spotter running on this device, we have to optimize it heavily to make it run with very low CPU and memory budget, and also runs with very low latency. At the same time, we need to make this keyword spotting task very accurate. By that I mean we have to make this very sensitive for our customers to use it very easily, even with different types of background noises. And on the other hand, we also want to have extremely low false accept to mitigate the privacy concerns, because our customers certainly don't want their speech to be streamed to cloud if they're not talking to Alexa. And this slide summarizes the architectures of a conventional HMM-based keyword spotting system. Starting from the left side, given this input audio stream, first we chunk this audio into a 25 millisecond window, and this window shifts with 10 milliseconds every time. Here we extract the standard FB features. FB stands for the log mile filter bank energies, which is a traditional acoustic features used for speech recognition. And here we extract 20-dimensional FB features for each window here. As a result, we would extract a 20-dimensional feature vector every 10 milliseconds. Once we got these LFB acoustic features, we will feed them into an acoustic model, which is shown in the middle part of this slide. And this acoustic model, the acoustic model could be a conventional feed-forward DNN, or for example, another type of neural network like time delay neural network, which will be focus of this talk. One thing I'd like to mention is when we feed these features into the acoustic model, we don't only fit the features from current frame. Instead, we also include the features from a few frames in the past and a few frames in the future to form a context window to provide more information for the acoustic model, make better predictions. This acoustic model outputs the posteriors for the eviCore phones, as well as other phones used to model the background. And the right side of this slide shows a conventional HMM-based keyword spotter. Here we can see it has two paths. The bottom one is a keyword HMM, which is a concatenation of the Alexa phones. Here I use Alexa as an example. And the other path is for the speech and non-speech background. Here it's simply a loop between these two states. And during this decoding, we would run the Viterbi searching in these competing decoding paragraphs between the keyword HMM and the background HMM. And each time when this decoding goes to the ending state of the keyword Alexa HMM, it will trace back to the beginning of the word and extract the hypothesized audio segment for the word Alexa. With this system also provides the likelihood of the Alexa word within this audio segment. At the same time, the system also provides the likelihood from the background model on the same audio segment. As a result, we are able to compute this keyword score as the log likelihood ratio of the keyword HMM versus the background HMM. When this keyword confidence score is larger than the predefined threshold, the system triggers. Any questions? Yeah.
So when you got a lot of data about how Alexa was said there. So can you tell if the speech is coming from the same person that said Alexa?
Yeah, I think the question is if we can do the speech, the speaker-dependent eviCore detection.
Well, you heard Alexa, so some one person said that.
Right.
Now, if a second person then says, "What's the weather?"
Yeah.
Are you able to realize that "What's the weather" is not the question?
Here, once the way Echo works is once this Alexa is detected, the channel will be opened, right? The stream will be uploaded to cloud. And when the second person asks for the what's the weather, if the stream is still open, the cloud will process this audio.
So you're not saving the side data. The data that detected was Alexa. It's a lot of information about the speaker.
Right. Actually, that's a good point. We also have the published papers from other groups. From the ASR team, for example, they call this anchored information, which extract these features from the Alexa part to use to improve the speech recognition for the speakers. That's a very good point.
How did you deal with things that sound very close to Alexa? You could have someone in the house named Alexa or Alex, or maybe they have a friend, they say, I gave Alex a gift. How did you kind of break that up?
Right. Yeah, that's a good point. And we call those the false accepts. And ultimately, we want to remove all of them. But certainly, it can be more challenging than other words because they sound similar to Alexa. Here, from this HMM-based keyword spotter I present here in our published paper, this background model, which loops speech and non-speech, will be used to model these confusable phrases. And even from the reality, those could give very close scores. It could give close scores to Alexa, but our system is robust enough to differentiate that's not the Alexa word. Still able to reject this. Yeah.
So, quick question. You chose 10 milliseconds as the windowing function. Like, did you experiment with other windowing functions or like that?
Right. I think those parameters could be tuned empirically with our data have, but this 25 millisecond window with 10 millisecond shift is very standard combination, I would say, used for the speech recognition in the speech industry. So, but those parameters can certainly be tuned. Yeah. Yeah, these 20-dimensional features extracted for each frame. I think you raised a good point if those could be rich enough to represent the whole speech frequencies or the information. And at some point, we have to make a balance between the performance, between this accuracy and also the complexity of the system. If we use much more dimensions, that certainly would increase the complexity to process those features. For your second question, this 20-dimensional feature will be combined with the other 20-dimensional features for the past frames as well as the future frames to form a much larger input feature vector to the acoustic models. Okay, let's go to the next section, which is about time delay neural network. Compared to the feed-forward DNN or the recurrent neural network, time delay neural network or the TDNN captures the temporal dependencies in a speech segment in a hierarchical fashion, which I will explain in more details later. It has relatively fast training time when compared to the recurrent neural networks. Because TDNN has tight weights, here we can use fewer number of parameters than the traditional DNN to model the same context of speech and obtain a similar performance. For example, this slide shows a typical TDNN architecture. And we took this picture from another earlier published paper from a academia speech research team. Here we can see the bottom part is for the input acoustic features for each frame. Here we take 13 frames in the past and 9 frames in the future. As we can see that in the first hidden layer, and they use only 5 contexts as input, different from the DNN, which would use all the whole context window as input. Due to this architecture, this TDNN uses its lower hidden layers to model a much narrower context to learn the transform invariant features. And when we go to the upper hidden layers, we see that starts to see wider and wider context. It turns out this hierarchical modeling architecture is very efficient to extract information from a much wider input context. And because this TDNN has tight weights across all the time, and it can be very expensive to compute these hidden nodes activations for every timestamp during each hidden layer. Here, I mean, if by definition, we will need to compute all these blocks in the light blue and compute all the lines for the TDNN decoding. You can see that's a lot of computation. And people have been finding that because there are lots of redundancies in the input due to the overlapping of the context, we don't have to compute the activations for each time. Instead, we can only subsample a timestamps during the hidden layers, which are labeled by the red blocks and the red curves. By doing that, we can remove the other parts and make the TDNN much more efficient during decoding. On top of this, we propose to insert bottleneck layers to the TDNN architecture. This slide shows the TDNN architecture used for our experiments. Similarly as the previous slide, we have 20 frames in the past and 10 frames in the future as the input context. And we can see that the first layer also takes 5 frames as input with 2 in the past and 2 in the future as the previous one. The different part is we insert the bottleneck layers for all these hidden layers, and which are labeled by the letters B in here. And the idea of the bottleneck layers shown in this picture, suppose the network has 2 neighboring hidden layers with dimension m and n separately. With the 4-rank affine transform, it will have m times n multiplications. By inserting a linear bottleneck layer, which are labeled by the red circles here, if we carefully choose its dimension r, we are able to reduce the multiplication from m times n to m plus n times r. That could be a big reduction. This bottleneck comparison has been widely used for the speech recognition, and it provides the regularization during the network training and helps the network to generalize better for the new data. Typically, people use the singular value decomposition, the SVD, of the affine transforms to initialize those bottleneck layers. In the next section, I will talk about the TDN training recipes. Here we use two techniques to improve the TDN training performance. The first one is called transfer learning. The idea is instead of directly training this TDN with the eviCore output phones, for example, starting with the pre-layer, the layer-wise pre-training, we first train the TDN with the same architecture but with ASR outputs. Once we train this ASR TDN, we use that one as the initial point to train the eviCore TDN. It has been shown that by doing this transfer learning, we are able to provide a better initial point by using the ASR network, and that helps to get a better local optimum. Another technique we use is called multitask learning. The idea is showing on the right picture here. We can see that here we have the task 1, that is the keyword output. That's the main task. Besides this, we also add a secondary task, which is the ASR output, labeled as task 2 here. By adding the secondary task, we are able to provide more regularization for this keyword TDN training and also helps generalize the network. During the multitask training, the losses are computed as a weighted interpolation of the losses from both keyword tasks and the ASR task. Empirically, we have been finding that it's best to have the last hidden layer to be separated for different tasks, with the lower hidden layers to be shared. As a result, our network has shared lower hidden layers as the feature extractor and have the last separate hidden layer and the output layer for different training tasks. To summarize our TDN training recipe is as follows. First, we would train a 4-rank ASR TDN, which has the same architecture as the target eviCore TDN. And this network has the ASR outputs. After that, we would add the keyword branch, which includes the a separate last hidden layer and the output layer with the eviCore phones. And we run multiple epochs for multitask training to optimize this network. Once this network is trained, we will insert linear bottleneck layers into these all 3 hidden layers, and those linear bottleneck layers are initialized by the SVD. Once we have this architecture, we would run another few epochs of multitask fine-tuning. Once this network is trained, the last step is to remove the ASR branch. After that, this network only has the eviCore output and can be used as the acoustic models for our keyword spotter. For our experiment here, sorry.
Sorry.
Yeah.
My question is, how do you know when to stop training this particular layer and then move on to the next module?
That's a good point. There could be different learning scheduling schemes. For example, some people, they use the performance-based. They would have a head-out dev set and measure the accuracy after every epoch, every iteration. And they will set a minimum learning rate until they reach that one, or they set max number of training epochs. Another method would be, for example, just set the constant decaying rate we just constantly decaying this learning rate at every epoch, and then we run multiple epochs. In our paper, we use the second one.
Okay. And also, typically, would you go back and retrain those previously trained way to improve the performance, or just like keep it set later on?
I'm not quite sure if I fully follow your question, but every iteration would be tuning this neural network weights, right? It's kind of improving during every epoch, every iteration. Yeah. Sorry.
Training data.
Yeah.
How did you wind up with the training data for this?
I mean, how did we get the training data?
You use a real Echo box, and somebody says Alexa, but it doesn't recognize it. You don't get anything. So
right.
How do you get training data?
I think you have good points. If those devices not activated, people don't activate the device, those data would not be collected. That could be a challenge for our work as well. Yeah. But there, on the other hand, there will be a lot of data available, right? Even though those might be cleaner or easier case. But there are some techniques to make them more suitable to treat the network, detect the harder cases with different background noises.
So how do you tell the structure? Like
Right. That's a good point. We spend lots of time actually optimizing this architecture. Mainly, we have very limited CPU and memory budget, so we couldn't have much very deep neural networks, so we cannot have very large hidden layers. But those from empirical tuning, I would say. I mean, we have some good intuition or some good knowledge about what type of neural networks or how many layers we could use from our previous experience. So, yeah. Okay, for our experiment here as baseline, we trained a DNN with 3 hidden layers. And this DNN is also compressed by the SVD. We have been finding that SVD compression could improve the DNN performance. So this DNN is a very strong baseline. It has 20 frames in the past and 10 frames in the future as the input context. Because we have 20-dimensional features for every frame, as a result, this DNN input would have 620 feature vector as input. And it has 55 as the bottleneck layer dimensions and 200 as the hidden layer dimension. After that, we trained 2 types of TDN. The first one, TDNA, that's without SVD compression. It has 5 frames as input. That's 100 dimension feature vector. It has 135 dimension in the hidden layers. After that, we also trained the second TDN, which is TDNB. It has similar architecture as the first one, but it has SVD compression. For example, similar to DNN, it has 55 dimension in the linear bottleneck layers. Because of this, given a fixed budget, we are able to, with this bottleneck layer, we are able to increase the hidden layer size from 135 to 193. And all those 3 networks share the similar training recipe, including multitask training and transfer learning from ASRDN to have a fair comparison. And all the 3 networks have similar size with less than 100K multiplications. To measure the keyword spotting performance, we use 2 metrics. The first one is miss rate, that's 1 minus recall. The second one is false accept rate, which is normalized number of false accepts. Here we are able to plot the detection error trade-off curves by tuning the transition parameters and exit penalties for the HMM structure. For example, our DET curves are shown in this picture here. We have this miss rate on the x-axis and the false alarm rate on the y-axis. Here we can see we focus on a very low miss rate range, less than 5%. We don't reveal the absolute number of the false accept rate. We only plot to a multiples of a constant number x. But as you can imagine, this x is extremely low number here. We have 3 curves. The black one is for DN, and the green one is for a TDN without SVD, and the red curve is for TDN with SVD compression. Because we have miss rate and false accept in both axes, the lower the curve is, the better the performance of the eviCore detection. And we use the area under the curve, the AUC, as the final number to measure this performance of all 3 systems. Compared to the DN baseline, the green curve, which has no SVD TDN, that already reduces the AUC by 19.7%. If we further insert these linear bottleneck layers to get the TDNB here, which is the red curve, that further reduces the AUC by 37.6%. That's a huge improvement in the eviCore detection performance. To conclude, here we talked about how to use the TDNs for the acoustic models to couple with a HMM-based small footprint keyword spotting system. We propose to insert linear bottleneck layers to the TDN architecture, and together with the temporal connection subsampling, we are able to significantly reduce the complexity of the TDN system and to make it running really fast on the device. And compared to the DNN baseline, here this TDN with SVD already reduces the HMM AUC by 19.7%. If we further insert the SVD compression, the TDN-based system could reduce HMM AUC by 37.6%. I would end my talk here. Any questions?
How do you come up with the bottlenecks? I mean, if I understand correctly, the bottleneck was supposed to reduce dimensionality. How do you come up with the bottleneck layers?
I mean, how do we come up with the dimension of the bottlenecks, or how we?
Both.
We borrowed this idea from the ASR field, and people have been using this to reduce the multiplications in their networks. Because typically ASR has very big network, and they would run this to reduce the output layer, which is the most computationally expensive part. But for our case, we have our most complexity during the hidden layers and the input layers. That's where we apply this SVD. That's the, I would say, one difference. But we borrowed this idea there. Yeah.
How much accuracy you lose when you use this bottleneck, teacher?
Sorry, could you say again?
How much you lose from the accuracy when you use this bottleneck?
Actually, in our comparison, we design our network in a way the TDN with or without bottleneck would have similar number of parameters. Because with the network, the bottleneck layer could reduce the number of parameters, we are able to increase this hidden layer size. That's how we do the comparison. And our experiment shows that this way we can get much better performance with the fixed budget.
So this question could be very wrong, but I just want to ask anyways. This is the first time I heard about time delay neural network, but I can see some similarity between convolutional network and this one. For example, that we have perceptive field that you only connect to a few input layers, and also the bottleneck layer, it seems to be a max pooling analogy. So first question, is that relevant between TDNN and convolutional network? And
sorry, go ahead. Actually, I think you raised a very good point. That's a great question. Here, this time delay network was proposed actually 2 or 3 decades ago. And with recent years, people have been finding ways to optimize it, for example, by doing the subsampling of connections to make it more practical to use. And for your question related to saying actually this, I would say we can treat this time delay neural network as a one-dimensional convolution across the time domain. That would be my understanding of this, because time delay neural network also has the height weights across the different timestamps. That's like a convolution.
Okay.
Okay, thank you.
So while we set up, let's just introduce. So my name is Afik. You will see this first slides in a second. Daniel Schoenfeld here will be presenting with me. We are with eviCore Healthcare, and we are going to share with you kind of from zero to where we are today, our journey with deploying machine learning, deep learning in our system. You will see in a second. We will first share kind of the principles, the way we operate, and then we will share with you. Thanks. Hello. Yes, and then we will share with you how it actually manifests in production, in the journey. So, are we ready?
Use this.
Okay. Thank you very much. It's a bit loud. Okay, so the title here is, surprisingly enough, it's not about deep learning, but don't worry, there will be deep learning, and Daniel will give you some of the details about that. But the really key point here is in this story, and I think that story resonates quite well with other healthcare companies. Just a question, who here in the audience is with a healthcare company or works with healthcare data? Okay, so we have quite a few. So some of the points we'll share here, some of the painful points we'll share here will probably resonate with you. So you will see that it's not really about deep learning from our standpoint. It's about the value and whatever it takes to get that value. And sometimes, kind of like in this story, deep learning is a good way of achieving that. So with that, the backgrounds are here. Sorry. Sorry. Hmm? Okay. Okay, good. So a couple of principles. We are about the business value of machine learning, deep learning in healthcare, and kind of at the top of it, everybody is talking a lot about replacing doctors with AI, replacing doctors with technology. We are not pro or against that, but we are trying to focus not on this hype. We realize that there are some things that nurses do in our company, and we'll explain those in a second, that can be much better done by technology. And these things we will replace or we will improve. But we try to stay away as much as we can from the hype. I actually think this is an older version of the deck.
Did you upload it?
Yes. Sorry, so I'll continue in the meanwhile, but while we are trying to change the versions, we go with very small iterations, and what we really try to do is we try to create a win-win situation with technology. And as you will see from our metrics and our business, this is not so trivial. It's actually not trivial and not possible at all without technology, without machine learning. And I think one of the key things and why we can deliver so much value, even mostly financial value, but also user experience improvement and provider satisfaction, improvement of care value because of it is exactly because the technology helps us create this triple win that without it it's impossible. Okay, so using technology for the win-win, we'll talk about that in a second. Let's talk about who we are, what we do, and then we'll start delving deeper into the problem that we're trying to solve, how we solved it, and what's the result. So whenever each and every one of you, and actually whenever a third of the population in the US needs some sort of an imaging or medical procedure done on them, you usually go to the physician, your physician or specialist, and he has to, let's say you injured your leg and he says you need a knee MRI or something like that, then that request will go from him, from the provider, backed by clinical data, your clinical data, to us, so we can watch and make sure that the clinical data really fits and it makes sense based on the best of evidence and clinical rules and so on, and that's the right thing, and approve that so it can be done, and then the insurer will pay for it, minus, of course, the co-payment and whatever else, but we're not here to talk about the problems and quirks of the healthcare system. So we do that, and we do that really at large scale. So 100,000 transactions a day, we employ 1,000 nurses to go through those. As you can see, the numbers don't match, so there needs to be something that helps those nurses and clinicians do that, and this is essentially us. And we really cover most of the US. So every request undergoes clinical scrutiny, and we'll talk about that in a second. The goals are here. And a couple of things that are important. Healthcare organizations have very, very low risk tolerance. And that is very, very challenging for a data science team. I see people nodding in the audience, and that's kind of the good and the bad things about healthcare. The good is the impact, the bad is essentially everything else. So that's what we work with. We have a unique proprietary data set of all of those transactions, and we of course use that, so it's huge, it's unique, it's not so simple to work with. Okay, so now that you know what we do, then the first questions we had, the first thing we think about is how do we measure if we are successful or not? Because without it, we are actually blind. And the two key things for our success in this project and in general are in this slide and the next one. The first of which is the metrics. And they are, by the way, very much tied to the bottom line of the company, the bottom line of the value proposition.
The metrics, first, appropriate utilization. How many of the requests that get to us are appropriately approved, or those that should not be approved get to a physician review, and then the physician reaches out to your physician and they discuss what's the right next steps. So there are some sub-metrics behind that, below that, but that's the utilization. The other one is self-service requests. The quicker the physician can get this approved, the quicker the physician can do it by himself, the better it is for them, the better it is for us, the better it is for you. Question? Okay. And there are two other metrics, and one of them is reducing the variation between clinicians. I am a physician, we have physicians, we have nurses. Unfortunately, when humans try to make clinical decisions, they don't always agree. That is generally not a bad thing, but it's definitely not a good thing. In our line of business, it's actually not good at all, and we've seen that if we can really narrow that, the quality overall of the decision increases. And lastly, and actually important, is the better user experience. Now, going back to the win-win situation, up until what we are doing, it was impossible to improve all of these together. So, for example, improving the user experience, which means doing things quicker, or improving the self-service, which means getting it done a lot quicker, essentially simply improving, meant that you lost something on utilization. You probably falsely approved some things. Now, not so much. We can actually optimize across all of them. Okay, so, and the other guiding principle that we have, and we'll get to the technical bit in a minute, is this is how we think about things. We iterate to maximize the fit between the data and the product. Problem or process depends on the use case, but in this specific case, this is what we call the product data fit. We have data, certain techniques that we use. This is essentially what's driving the accuracy of the model. And we have the problem that we are trying to solve. One of the key things that you will see here, and we see all across the industry, especially in healthcare, but not only, is that oftentimes people are focused on this part only. And this part, optimizing it, it's actually really hard, especially if you're not Amazon, if you don't have the data, if you don't have the service, especially if you are in healthcare and you're stuck with limited, noisy data sets. So improving this is hard, but improving this, or changing this actually, it's hard, but it's doable. And if you do it, you're making your life and you're making your solution a lot easier. We gave some examples here of what it means downstream impact and what it means problem difficulty. But essentially the idea of downstream impact is if you're doing something and it's not so actionable, so you give a great recommendation, your model is amazing, but the physician says, you know what, that's a great recommendation, but I think differently. So, okay, you've done great, but you haven't really created too much value here. Or if you have a problem where the cost of error is really high, this type of a problem, and not everybody gets to 100% accuracy. Actually, most people, especially at the beginning, gets to like 60% accuracy and then start improving from there. If you have something that the cost of error is so high in that performance, that means that you have a really difficult problem. And you might as well try to think about this, if you can, of course, about a simpler problem to solve, and we'll give an example of how does that look like in practice in a second. So kind of this approach is playing with the problem is actually really helpful, and this is a good, in our opinion, rule that we use in order to make decisions and decide on the next iteration, the metrics and that. Okay, so now let's get to define the problem and define what we were trying to do. So this is the process that we have. There is a user input. It's mostly clinical. It's questions, what happened, what the injury, what was done so far, and a couple of other things that are relevant for a medical condition. Based on some of that is immediately approved. mostly things that are urgent and these type of things. Some of that goes to a nurse review, the nurse can improve. Some of that goes to a physician, the physician can improve. And some of that is not approved. Okay, and when we started, this was the process. It still is, but more sophisticated. And there were not too many metrics of how this process is working, especially not too many metrics of how the nurses are working, what's the variability between them, how the physicians are working, what's the variability between them. And I'll tell you, it's high. And there were lots of edge cases and lots of weird things that we've noticed. So this was the initial state when we started. And then, okay, and then we said, okay, given that, you remember that rule that we shown, what's the data, what's the techniques, what's the problem? We don't know much about them. When we started, we didn't know much. So we did an experiment. We say, let's try to learn how all of those things, what's the cost of error, how much data we have, how good is that data, what's the SNR, and all of those type of things. So we did the first experiment. It took us 3 months. We had something working at the end. Performance was okay. It was mostly machine learning. Daniel will describe the exact details, but we added machine learning models at this step between the user input, between the nurse, and we said, you know what? Maybe the machine learning can prevent cases from getting to the nurse and say, you know what, that case is highly likely to be denied by a physician, so it should skip the nurse. Or that case looks really good. It's probably fine, even though this system did not approve it. It's probably fine, it should be approved. That was the experiment, and we kind of went blind. We didn't know much about what to do, but we knew that we would learn something. We actually learned quite a lot. Now, I'll let Daniel take it from here to explain it more, and I'll be back.
Thanks, Afik. So I'll do the more technical part, and this is still going to be fairly shallow. When we get to the later slides, we'll go a little bit deeper in terms of the architectures. System. It's fine. Okay. So basically, what we're building here is a set of machine learning models. We're talking about hundreds of them because for each procedure, there is a different model that take historical data about that particular procedure, lots of cases that were performed in the past, and what did the nurse do with them. And using that as a label training data, so pretty vanilla supervised learning problem, and we use really simple models. So anything you can find on scikit-learn, your regression models, your tree models, and so on and so forth. Turns out that for different procedures, different types of models are more performant. So you'll find some where some sort of logistic models, usually with some L1 regularization, are more performant, and you'll find some where sort of gradient boosted trees are more performant. But in general, pretty vanilla. And it was also pretty clear that there's a ceiling of the performance here, mostly because the quality of the data is just not great. As Afik mentioned before, it's hard to measure the variability on the performance between the clinicians, both nurses and physicians. There were many other things that are hard to measure, and so we're kind of in a garbage in, garbage out situation. So it became pretty clear that we can't go from here to deep neural nets. The performance is not going to improve. That's again the sort of framework that Afik presented earlier. If you're not solving the right problem, you don't have the right data, then the value of what you're going to produce is just not going to be that great. So a couple interesting points here are, how do we know how we're doing, right? So we have hundreds of, tens of thousands of cases a day. For each procedure, it's maybe a few thousand. And we want to make sure that our performance sort of maintains a certain level as time goes by. And things do change. So sometimes the clinical guidelines change a little bit. Sometimes the different clients have different rules and expectations and so on. So what we do is maintain an audit, basically. So let's say 90% of the cases, if the model is able to make a decision, it will make the decision, but in 10% randomly, the case will still go to a nurse. If the model is not able to make a decision with enough confidence, so it's pretty clear that the case should be approved, great. Pretty clear that the case should go to a physician, fine. If I'm 60, 70% sure, maybe I still want to show this case to a nurse. But as I said before, we do maintain an audit even in cases where we're fairly confident, and that provides us both with additional training data to fine-tune our models as time goes by. We usually train them, so this is not Amazon, we don't retrain them daily, more like monthly. There's also an interesting problem here. So we have hundreds of models in production, as I mentioned, and this is very far from what Amit detailed previously, but these models are kind of coupled, right? So if the performance on one of the types of procedures is going down, it may very well be going down on other procedures, but maybe not, because I do have a few hundred models in production. So if I wake up today and one model is performing better or worse than average, but with a p-value of 0.01, it's kind of to be expected. So there's some interesting stats here coming in when we're talking about how do you monitor the performance of the model, and how do you make sure that they're at the level that you expect, and so on. Still, in terms of the performance, we're able to make a determination about maybe 30% of the cases that we're seeing that are not completely obvious. But it's not quite at the level that we want. There's a ceiling. Any questions before we return to Afik? Afik?
Yes. Which slide? Okay. So kind of to summarize what we learned and what... sorry. Yes. Yes, of course.
I mean, my question is on the data itself. It seems that you are, I may be wrong, that you are a lot more biased in approval rate. So you tend to approve a lot more often than denial. So the question is, what's the objective of such retraining? Are you trying to use the data as is and try to basically bypass the reviewing process, or are you trying to train the model to optimize the
Yeah, so that's a very good question. You're right, most cases get approved. And that's a good thing, right? You don't want to go to the doctor and the doctor says, oh, you need to get an MRI, and then 50% of the cases, it turns out that it's not approved, right? So you're right that this is an imbalance problem. Most of the time, cases are approved. So there are two things to think about here. One is that at this level, the problem is a little bit less imbalanced, right? So the model here is trying to emulate what the nurse is going to do. And there's still a chance that the nurse will pass the case to a physician and the physician will approve it, right? And so at this point, you're less biased towards approval. The problem is still imbalanced, and so there are various things that you can do, upsample and downsample and so on. There's also a sort of the levels of performance that you're thinking about are actually set by the business. Right, and so it's okay to be biased towards approval, and to a certain degree, a certain level of statistical bias is acceptable here.
How do you know when you've made a mistake?
So, on the training data or in practice? Okay, so on the training data, you reserve a portion as test data. The training data is well labeled. That's kind of standard vanilla. If you're approving a case and the case should not in fact be approved, you have no good way of knowing that. But we track the performance using that audit portion, right? So on 10% of cases, I actually make a prediction and I see what happened downstream. Did the nurse approve? Did the doc approve? Was the case deemed inappropriate? So you do have that level of control over what you're doing. And in fact, you have a whole level of different settings for the models that you can say, well, I'm willing to accept this many false positives.
For the user input, is this like something that's coming through a system, and is it like HL7 or ICD-9, or is it something biomarkers in the lab?
Excellent question. So in this case, it's primarily user input. People, like a physician or someone, their staff will log on to the eviCore website and submit a lot of information. It's a combination of structured and unstructured information. So you're going to have some demographics, you're going to have your ICD-9 codes, your CPT codes, and so on. That means what kind of diagnosis, what kind of procedure is the physician requesting, plus a lot of free text. We are starting, and this is actually happening now, to get data directly from the patient medical record. So yeah, there is an HL7 integration portion and so on and so forth. By the time it gets to the models, the data has been sort of consolidated into one format.
Is there any feedback to prescribing doctors? I mean, like, other than that, to approve or not approve? Because, like, it would be valuable, I think, to doctors to know exactly if it was not approved. Why?
Yeah. So this masks some of the complexities of the process. You'll notice that at this point, the models aren't making sort of non-approval decisions. They're leaving it to the physician. And that's by design. At that point, the physician may very well pick up the phone, and so this is the eviCore physician picking up the phone to your doc and having a conversation. Is an MRI really the right thing in this case? Maybe we should think about something less intrusive, less expensive, less complex, or yeah, maybe it is the right thing once you have the conversation. So I'll take one more question, and we'll move on, and we'll have more questions at the end.
So that's about interpretability. So how does the physician have confidence?
Very good question. And this is another thing to keep in mind if you think about the problem difficulty, right? If your models have to be interpretable, you're kind of handicapping yourself, and a lot of stuff is maybe out of your domain or you can't really use. In this case, if I'm approving a case, I don't need to provide a reason for that. And if I'm sending the nurse to a physician, I don't even have to tell the physician that this is coming from the model. The physician is going to review the user input and make their own decision. Sometimes you don't even want to bias them, right? You may or may not want to tell the physician, hey, a model here thought that this case is likely inappropriate, take another look. You may or may not do that, depends on the procedure, depends on various other factors. So it's actually, in terms of the problem that we're trying to solve, it's a good feature here that interpretability is not something very important. We'll do more questions at the end.
Okay, then if you can just next slide. Okay, so just to recap, we started with the process, we did an experiment, we learned a lot. Now let's see what we've learned and how we proceeded. So we deployed those models, took about 3 months, what Daniel described. And then we learned a lot of things. The first thing we learned is about our process, the eviCore process. And we learned, at least from the, I would say, analytical lens, is that it's suboptimal. Okay, suboptimal from the user experience standpoint, suboptimal from the performance standpoint, from the variability, and many, many other factors. We've also learned that a lot of what our nurses do, and nurses are clinicians, they are paid well and so on, they actually handhold the users throughout the process, and a process that should be self-service. So there is something wrong here, and we'll discuss that in a second. And we also learned that the data, we had tons of it, as we said, but like Daniel also said before, is most of it is in poor quality, so kind of gets us to the garbage in, garbage out type of problem. Now, we also saw we had legacy systems that this was all on. So they weren't tracking a lot of the data that we wanted to improve, or at least to know how we perform. And it was impossible for us to actually track what's the user journey in the system. So Amazon, for example, when I enter the website, they know exactly what I'm doing every step of the way, and they can improve accordingly. We had nothing. And that actually, one of the things that really were critical. What we realize is that right now we do not, what we try to do with the models between the user input and the nurses, this problem that we try to solve with advanced analytic, not the right problem. We need to take a step back and rethink about the problem, so then we can deploy analytics in a way that will actually improve. So we thought, we talked with people, okay, and we came out with a plan. And the plan had two parts. First, we are going to completely change the process, at least the technology that's running the process. And we will change the process so it will be simpler, it will be easier. The nurse will only take the complex cases where their clinical judgment is really necessary, and we will use the process, we will change it in such a way that we will maximize the amount of data that we are collecting from the users, which is unfortunately not something we did in the old process. Now, people that know the industry, so we were new to this, kind of warned us that making the process simpler and easier might be risky because, once again, we were naive, but they told us that some people are trying to abuse the system and trying to really ask for cases that should not be asked for and not even presenting clinical information to back it up and so on. Now, I don't even want to talk about the health risks in that as a clinician and the fact that it's fraud and so on and so forth, but this is a risk the risk of abuse can increase. And not only that, so there are other risks that tie to that can, I'm not saying increase, but can definitely become more clear. So that's the process part that we said we'll fix. The data part that we said is we will now have complete control of the data that we will collect. We will maximize the amount we collect. We will have complete control over it. The system will be ready to start connecting it with models, kind of like what we've showed before, but more sophisticated stuff. Daniel will get to that in a minute. And we will also build it in such a way that we will be able to control the UX, give notifications to the users, guide them through, give explanations to the physicians what they're doing wrong, and so on one hand. And on the other hand, in the inputs part, we will be able to hook the architecture, the system directly to the EHR, pull the data from it, and actually save a lot of time for the physician office, because as you know, they do not have much time on their hands. Okay, so what we essentially did is we created a new process, we simplified it, and made it very two-step process, very simple. It took us 4 months to completely rebuild the entire technology stack, UX, UI, backend, everything for it, and we started measuring how we perform. And all of those metrics that we've discussed before, we saw how they were. So we did a pilot with 3 stages. The first stage, we just watched. We let users go through the system. We very closely monitored what is happening. And we already saw improvements in all of the parameters. We had a very granular profile of their behavior, kind of like the Amazon knowledge of people in their portals. And then we said, okay, now that we've seen how people use the system, and we actually saw that there is some problem of abuse, and there is some of the people that are trying to get approvals for things that are really unclear, then we started saying, okay, let's start more actively add friction into the process and see what happens. And the first step of doing that was kind of like applying friction all across the board. And that is annoying to people, of course. And second, it's it was effective, you will see in a second, but this is not sustainable. So we need to find a way to apply friction in a much smarter way. And this is slowly becoming a problem that we can actually solve with technology. So the new paradigm we came with is trust but verify. And Daniel will take it from here and will explain how we started executing on that problem.
Thanks. So from a user's perspective, what's happening now in the system is that you say, all right, I want to perform this procedure, here's the reason, and here are the clinical reasons that this procedure is appropriate. And we say, okay, but give us some evidence. And please make this evidence come from the patient's record. Copy paste. This is, as Afik described, in the kind of very high monitoring, high surveillance regime where everybody gets to give us a lot of evidence. You can think that downstream you can do it by having some sort of a prior about how trustworthy this user has been in the past and sort of the real-time behavior. Did they actually paste something? Are they typing? Did they go to some other window or not? And so on. So the front-end tracking can do a lot for us here. The sort of a little heavy-handed, everybody has to give us a lot of information, which also gives us a lot of training data, took maybe 1 month to implement, so that was fairly quick. And then you can start looking at the evidence that people provide. And you'll see that whereas some people thought that people write sort of nonsensical things about Humpty Dumpty and so on, that doesn't actually happen. So some people will say that the evidence is not available, and that's very easy to filter out. But otherwise, that's not what bad evidence looks like. So what's the problem that we're trying to solve now? So we have a question that we're asking the user, and we have a piece of evidence that the user gave us, and we want to decide, does this evidence support the question? So to make it really concrete, question really looks like, does the patient have some sort of a condition, seizures, and you expect good evidence to look like patient is 35-year-old male, presents with seizures, blah, 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 so on and so forth. So intuitively, it contains all the information that's contained in the question, and then some. And that's what you're trying to detect here. You could think, well, if I have this question about seizures, and I had thousands and thousands of people answer that question, maybe I can build an individual model. But really, it's better to build a more abstract model of, given a question, given a piece of evidence, does the evidence support the question? There was a question here about, do we get the data from the EHR? And so this is a good stepping stone towards the kind of next step here, which is already in production, but it's kind of a bigger project of getting evidence directly from the EHR, so we don't have to burden the user with give us evidence. And moreover, it's much more reliable because it's actually documented in the medical record. So we have a good problem here to solve. But do we have good enough data? So this was a pilot deployed for a few procedures, and it took us a few months to develop it, so it's been in production for, I don't know, since earlier this year. So we have about 20,000 question evidence pairs. All right, we're not even talking MNIST level of data here. So in terms of scale, we need to take everything with a grain of salt, both in terms of overfitting, in terms of, we can't have huge networks. We're going to have to help them a little bit with some feature engineering. The good part is that it turns out this data set is relatively balanced. I don't know if you would expect people mostly to submit good evidence, but people submit a lot of bad evidence, and mostly it looks like just irrelevant. So you ask, does the patient have seizures? And they start telling you something about a patient who may or may not have seizures, but presents with some other condition, completely irrelevant to the question. The other type of bad evidence is, does the patient have seizures? And the evidence is, patient has seizures. right? So that's kind of not enough. So we want this Goldilocks situation where there's just enough information to capture what's in the question, to add a little bit to that, but not too much. We experimented a little bit with adding some, well, we have all this question and evidence. A good example of bad evidence is just matching the question with itself, or matching the question with evidence for some other question, because that kind of looked like this clinical but not relevant. And that adds a lot of data at the expense of making the data set more imbalanced. So we need to be a little bit careful here. Before we dive into the architectures, again, if we take a step back and think about the problem that we're trying to solve from the product perspective, what am I doing here? I'm asking the user to provide some evidence. And initially, especially when I'm training on 20,000 samples, my model is likely to not be very good. Maybe something like the blue line here. This is a dummy model, not really trained on anything. With an AUC not so great of 0.68.
You have a model that tell whether the evidence is
Mm-hmm.
relevant or not. So would you say that not relevant evidence is also in the bad category?
Yes, in this case, yes. Right, because I need the user to convince me that, yes, the patient actually has seizures. All right, so if they're telling me about some other condition that the patient has, it's not helpful. Which goes to the point that, and that's a very important point, most of these cases are not people trying to defraud the system. They're people who don't know exactly what they're doing. So it's not the physicians, it's someone on their staff, it's not a clinical person, maybe they're a little bit undertrained, maybe they don't really understand what we're asking them about. That's usually the situation we're dealing with. So back to here, we have a classifier that tells us whether or not evidence is good or bad. And let's say this is not a very good one, like the blue line here. What I could do is basically tell the user to give me more evidence. All right, so you answered 3 questions about this case. Question 1, 2, 3, I requested evidence for question number 1. If I'm not confident enough that the question is, that the evidence supports the question, I ask you for another one, and I run my classifier again. And maybe I do it a 3rd time. And by the 3rd time, you mix these 3 classifiers with a really simple naive base, and you're at an AUC of 0.8, so we're starting to get somewhere. Right. So essentially, I shifted the burden of uncertainty from my modeling problem and building a model, which is hard, or having to show the case to a nurse, to the user. So from a product perspective, this is great. From the user's perspective, well, hopefully it teaches them to provide good evidence. So next time, they get a better user experience. So we start with some baselines, kind of a bag of words approach. You take the question, you take the evidence, look at the Jacquard distance between them. It's a nice thing that these days you can talk about sort of embedded word embeddings and embedded documents as part of your shallow or strawman models, right? So you could think about, I take my question, here we trained on a clinical corpus that comes from WebMD or something like that. You embed the questions, you look at the question as embedded words, at the evidence as embedded words, and you can think about, well, let's look at how far the centroids of the questions and the evidence are from each other. That turns out to be not so great. You could ask, I want at least this much of the evidence, I don't know, 30% of the words in the evidence, but not more than 90% are actually close enough to something in the question. You get reasonable performance, like AUCs of 0.7. The metric we really care about here is something like, what's the recall at some level of false discovery rate? Right. So if you provided bad evidence, what's going to happen? If I decided that you gave us bad evidence, I'm going to ask for more. Well, if you really gave us bad evidence, I'm fine with that. If you gave us good evidence, that's bad user experience. So let's say I'm willing to tolerate that about 20% of the time. So that's where this metric is coming from. 80% recall at 20% false discovery rate. This number is sort of product determined. And it's an important point that the metrics that you really care about, they're determined by the business, by the product.
So there's kind of a feedback loop here that it's different from a lot of machine learning problems. If I was the doctor, it's only advantageous to me if you prove it, right? It's a negative to me waste of time if it's not approved.
Right.
The doctor, is issuing probes into the system to try and maximize approval rate.
Mm-hmm.
And so as soon as one thing is approved, whatever the input was for that, it's going to show up on the next patient. Right? Doctors, presumably over time, the doctor's approval rate should hit 100%.
Ideally, but in practice, no. So there are various reasons for that. But doctors, even very good doctors, won't get things 100% correct every time.
Well, but aren't they going to realize that the last time they put these sentences in, it was not approved, so they have to change it?
Yeah, so that's verging on perjury. So right, the very few people will actually lie.
Well, it's not a lie, right? It's different kinds of evidence. You're saying, like some might be.
Oh, if you're writing something about a different patient, about this patient, that's perjury. Okay, that you could lose your license over that. So if we were able to detect that, the government will take care of that. So one last shallow model that still relies on these word embeddings is I could look at for each word in the evidence, what's the closest word to that in the question, and look at the similarity between the two. And now for each, for each token in the evidence, I have a number, and I can look at the top k of these. I think we take 15 or 10, I don't remember the exact number, throw in some additional features and regress, and that actually performs pretty well. How much time do we have?
I think we're over time.
We're over time. Oh, so we're not going to talk about deep learning then. I'll go quickly. For the deep models, and this is a lot of experimentation, we don't have a lot of data, so we need to be relatively careful. The type of question kind of looks a little bit similar to proposing answers to questions. So this architecture is from a paper by IBM Watson. Basically, it's the same idea. You embed the question, you embed a potential answer, you run it through something. So in this case, they're using a bidirectional LSTM with a convolutional net on top of that. You can play with lots of different architectures, and we've tried different ones. Ultimately, it's some sort of an encoder, decoder, or some type of you can think of the question as some type of a compressed version of the evidence. So it kind of comes from this circle of ideas. We played with, again, different things here, LSTMs, CNNs, and so on. For these types of models, the convolutional filters work best. But we're kind of on par with the shallow models. Not super surprising given the relatively low amount of data. So, well, maybe you want to do a little bit of feature engineering. And what you're kind of lacking here is something that will connect the question to the evidence more directly. And in this case, you usually like to use something like an attention mechanism. And so, inspired by that idea, so an attention mechanism basically takes some information from some place, some other place, dots them, sometimes add some additional linear operations, but basically it gives your, excuse me, it gives parts of your network information from some other parts of the network. In this case, evidence from question. There's been really interesting work. This is a recent paper, Attention is All You Need, from Google, that essentially replaces RNNs and CNNs kind of wholesale with just attention mechanisms and really improves on some of their translation tasks. So basically what we do is the same idea from the shallow model before. Take a word from the evidence, a word from the question, dot them, and now you have some sort of a two-dimensional thing. Here's the question axis, the evidence axis. each of these guys is a similarity between the two. So you can run some convolutional net. You get some interesting filters that kind of capture how information in the question propagates in the evidence, right? So not all of these make sense, but some of these are relatively interesting. Ultimately, it improves the performance up to an AUC of about 0.86 with almost 90% recall at that 20% level that I described before. Again, take it with a grain of salt because the amount of data that we have is not that high. But it certainly points the way towards, yeah, we can probably do a lot once we collect more data to solve this problem. And I think it's an interesting problem. So I'll just conclude. So what do we want to do next? Well, we want to get a lot more data. There's a lot of context around this data, right? So on top of what the user entered, we have their mouse clicks and their which questions they answered and their historical performance and so on, which at some point we would like to bring into the equation as well. I think this is an interesting problem, and also from a more sort of strategic corporate perspective, with this eye towards we want to use a lot of EHR data, gives us a lot of training data for what things would look like once we start getting data from the EHR, which we already are. When we're talking about in production, actually the relatively naive models are maybe good enough for now. So in terms of, well, I have these nice fancy models that I built on 20,000 samples. I'm a little bit worried about overfitting there, so I'd rather deploy the simple models and kind of keep testing them or keep testing the deep learning in the background. You want to do the closure?
Yeah. So just to wrap up before we get to the happy end. So going back to this principle of win-win, so we saw that with this technology, we can improve the user experience for most people, for almost all people, except the ones that are trying to defraud us, which will get some multiple requests for evidence. So they get a much quicker, much better response. Now, the self-service is also on the rise. The false approvals is not. So the utilization is kept at the right level and is even improving. So something that we could not have fixed without that technology, we were able to fix with that technology. So how does that translate into money? Actually, very easily. So self-service requests, better turnaround time. We have contracts that say that we need to get answers back within a certain time window. So that means that has direct connection to the bottom line of how many nurses we need to hire when we take new contracts. So we can now take new clients, and instead of hiring additional 100 nurses, then we can maybe do it with 50 nurses. Now the salaries of 50 nurses is a big difference. We don't fire people, we don't replace people, but this allows us to grow. We can grow as a technology-enabled business and not as a services business. The impact on the multiples on the bottom line is huge. And we are already for this year approximately 50% beyond the forecast that we had in terms of performance. So kind of like Daniel said, we are using that for the EHR data as well. It's important to say that eviCore has other service lines, other products that are also clinical, also the same ideas. We are applying the same technology there as well. So I think in addition to the fact that it is an interesting problem from the data science perspective, in my opinion, it's a very interesting problem from the product standpoint and also from the kind of AI in healthcare in general standpoint. There are not many projects which actually show such strong ROI. There is lots of promises, lots of hopes, but not very few products, very few projects that actually save a lot of money or improve a lot of process in a day-to-day. We hope there will be more, and this is why we are going and sharing and trying to share our experiences and what worked for us with others, with the hope that it will work for others. We'll be in conference in New York next week and in other places, and we'd be happy if you reach out and ask any questions. We'd be happy to answer. You'll have the emails at the end of the last slide. Thank you very much for your time and questions. If you have any questions, we'll definitely happy to answer now or later.